Hey, I am wrapping up week 2 of laser research. So we're working under a couple of postdocs who have a project that they're working on, and they just got back on Monday, so we actually got to start working in the lab. There's a lot of information that I've learned in the last couple of weeks, as you can probably imagine. So I think I'm going to just go ahead and walk through the lab itself and show how all the pieces fit together, and then hopefully I will come back and be able to explain individual components as the weeks go by and as we spend more time focusing in on different things that we're doing. Alright, so take a look at the lab. It's a pretty complicated optical setup, but all the pieces do fit together and they do make sense. So this is where the laser originates. There's a resonator in here that actually makes the laser beam itself. Over here under this panel we've got the amplifier, which is making the laser beam a lot stronger so that we can actually work with it. It comes out over on this side. Hard to see, let's flip it around. Okay, here we go. Here we've got a system of lenses and different things that basically focus the beam so that it's very, very, very intense on a very, very small area. Once it goes through this, it needs to pass through a vacuum chamber. Everything needs to be in vacuum because the beam is so strong, if it hits the air, it turns it into plasma. There's the other side of the vacuum tube. The beam is going to pass through this fiber. And this fiber is basically to spread out the frequencies that are being generated. So instead of just one frequency, it's kind of a wider spread of frequencies. I'll talk a little bit more about why later on. But then that needs to be focused onto a very, very short pulse. So a few femtoseconds, basically. A femtosecond is a trillionth of a second. Using those mirrors, it'll then pass into some other chambers. So in here there's a gas that when that beam hits the gas, it makes the molecules vibrate in a way that you get really, really, really short pulses. And then there's this piece which actually filters out the visible light, so you're left with just the really high frequency, high energy stuff, the really, really short pulses, which is kind of what we're aiming for in this lab. We're aiming for attosecond pulses. That's a billionth of a second pulse. There's a mirror in here. You can see kind of a gold mirror. That's to focus down the beam. And then those pulses need to keep passing through vacuum until they hit a sample. And what we do is basically something called a pump probe experiment. I'll probably talk more about that in future videos because that is much more intensely related to quantum mechanics. Over here is where then you're going to send your results into a diffraction grating so that you can see what frequencies you're getting, and then it's analyzed by these computers and devices. And if that's feeling like a lot of information, imagine where we're at, because now we're having to work with it. The challenges we are facing this week is that, you know how I said the beam needs to be in vacuum? Well, it's not right now because there are leaks in the equipment, so we can't get it down to vacuum, so we're trying to find the leaks. There's been some issues with alignment, equipment not fitting where it's supposed to go, so now we have to like redo all the mirrors and make sure they align. I'm not sure exactly what the goals are for next week or the timeline for this kind of thing. I can see that like you can spend hours aligning just a fiber. We had an issue where the fiber was burnt, and so we bought a new fiber. Now we have the new one in, so that's good. More adventures to follow. Stay tuned. Next episode will be released next Saturday. See you then.